Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
The unsung hero of particle physics, how George Zweig's quark theory changed everything. You know, while Einstein and Hawking made their loud entrances into the world of physics, you might never have heard of George Zweig. Yes, you heard that right, he proposed a theory that completely revolutionized particle physics, yet it was largely ignored by most. Today, let's step into the story of a forgotten hero in science. His theory laid the foundation for the particle accelerators you see on TV today. You've probably heard of quarks, but do you know who came up with the idea? George Zweig was born on May 13, 1937, in Detroit, Michigan. Detroit, the heart of the American auto industry, hardly the place you'd expect to launch a career in science. Unlike other famous physicists, Zweig didn't come from an illustrious background. His father was a businessman, and his mother a homemaker. But from a young age, Zweig had a deep passion for science. Though his parents supported his interest, they never imagined that, decades later, George would be the one to spark a revolution in the world of physics. Zweig completed his bachelor's degree at the University of Michigan, then moved on to the University of California, Berkeley, for his graduate studies. By 1961, he had earned a PhD in theoretical physics, though at that time, no one knew he was about to propose a theory that would change particle physics forever. In 1964, Zweig introduced a groundbreaking idea, the quark model. You know, quarks are the fundamental building blocks of particles like protons and neutrons. Zweig imagined these particles as invisible little pieces like the invisible man of physics. He proposed that protons and neutrons weren't the ultimate building blocks of matter but were made up of even more basic particles, quarks. This was one of the core problems of particle physics. If protons and neutrons aren't the fundamental particles, then what are they made of? Zweig, along with Giordano, almost simultaneously proposed the idea of quarks. But Zweig's model went a step further, emphasizing the role of strange quarks, which could explain some of the puzzling strange particles that scientists had trouble understanding at the time. Interestingly, the quark model didn't immediately win over the scientific community. You can imagine that when scientists first heard about invisible particles, they were a bit skeptical. After all, physics had always been about proving theories with experimental data. Despite the doubts, Zweig didn't give up. He stuck with his theory, but at that time, Giordano was the one who became more popular, eventually winning the Nobel Prize in Physics in 1970. In 1968, experiments at the Stanford Linear Accelerator Center, SLAC, finally provided experimental evidence for the existence of quarks. Yes, even though Zweig's quark theory wasn't widely accepted at first, over time, the theory was validated. Through high-energy particle collision experiments, scientists found indirect evidence of quarks, confirming that Zweig's theory was spot on. But here's the kicker: despite all this, Zweig still didn't receive the recognition he deserved. Unlike many theoretical physicists, he wasn't interested in fame. In fact, he couldn't have cared less. His goal was to push the boundaries of science, not chase after awards. Later on, Zweig shifted his focus to computer science and artificial intelligence. He didn't just rethink the fundamental problems of physics, he also made contributions to machine learning and neural networks. Yes, the same guy who turned particle physics upside down ended up delving into computer science. Throughout his career, Zweig maintained an independent and humble approach. While many scientists were fighting for recognition, he stayed focused on his passion, deeply immersing himself in the fields that intrigued him. Many of his contributions went unnoticed. On a personal note, Zweig kept his private life low-key. His wife and 2 children rarely appeared in the media. His love for his family and his dedication to science became the 2 pillars of his life. Today, although George Zweig may not be as well known as some other physicists, his quark model has deeply shaped modern physics. Every time a particle accelerator runs, every high-energy particle collision experiment, it's validating Zweig's theories. Zweig didn't care about the awards. Everything he did was for a better understanding of the mysteries of the universe. And today, we are living in the world shaped by his groundbreaking ideas. As the saying goes, still waters run deep. Zweig may have kept a low profile, but his influence continues to ripple through the world of science. Alright, let's kick things off and talk about today's main character, a young man from an ordinary merchant family who would go on to become one of the most revolutionary figures in the history of physics. The story of George Zweig might just remind us that great scientists aren't always destined for greatness from the start. Zweig's early life wasn't exactly remarkable. Born on May 13, 1937, in Detroit, Michigan, a city known for its booming automobile industry, Zweig came from a modest background. His father was a businessman, and his mother a housewife. There wasn't much of an academic atmosphere at home, and for many, such an environment might not seem like the breeding ground for a future scientific giant. But George had a different spark. From a young age, he was deeply fascinated by science. Unlike other kids who might be into sports or toys, Zweig was always flipping through science books, particularly those on physics and mathematics. He was endlessly curious about the world around him, always wondering how things worked. Though his family didn't have a rich academic background, they supported his dreams of science, encouraging his studies along the way. After graduating from high school, Zweig headed off to the University of Michigan in 1955 to pursue his college education. He chose physics as his major, and it didn't take long for him to stand out with his exceptional mathematical talent and logical reasoning skills. These skills would later provide the solid foundation needed for his graduate work. Physics was, and still is, a demanding field, but Zweig's persistence and passion for the subject allowed him to dive deep into it. In 1959, Zweig graduated with a bachelor's degree in physics from the University of Michigan. But he wasn't ready to stop there. He decided to continue his studies at the University of California, Berkeley, one of the most prestigious academic institutions on the West Coast. This was the place to be if you wanted to be at the cutting edge of science, and Zweig was determined to explore the frontiers of physics. At Berkeley, his academic journey really began to pick up speed. In 1961, Zweig completed his PhD under the guidance of physicist Melvin Newman. During his PhD, he began to explore the frontier issues of particle physics, setting the stage for his future groundbreaking research. Berkeley was a vibrant environment for physics, challenging, yet open to new ideas. It was here that Zweig started focusing on the most fundamental questions of particle physics, particularly those dealing with the most basic building blocks of matter. At that time, the scientific community hadn't yet reached a consensus on what the most fundamental units of matter were. Protons and neutrons were considered the smallest particles, but they too seemed to be made of smaller components. Zweig began to wonder, what if there were particles more fundamental than protons and neutrons? After earning his PhD, Zweig didn't slow down. He delved deeper into particle physics, and with his growing interest in the field, he began collaborating on larger-scale academic projects. His research soon shifted towards understanding the fundamental components of particle physics, those particles that make up atomic nuclei. And as they say, the rest is history. Zweig's curiosity and drive would eventually lead him to propose the quark model, a theory that would forever change our understanding of the universe. But all of this started with a curious mind, an ordinary background, and a deep love for science. Sometimes, it's the quiet, persistent pursuit of knowledge that leads to the greatest breakthroughs. You see, great oaks from little acorns grow, and Zweig's journey is a perfect example of that. In 1964, George Zweig introduced a theory that might just blow your mind. Imagine a groundbreaking idea that barely gets any attention at first, only to be confirmed years later as one of the most pivotal revolutions in the history of physics. Today, his quark model stands as a cornerstone of particle physics, but back then, it didn't create the kind of buzz you might expect. In fact, many in the scientific community were skeptical. But Zweig never gave up, and in the end, his foresight turned out to be spot on. Zweig's quark model, first proposed in 1964, not only completely changed our understanding of the structure of matter but also opened up an entirely new door in modern physics. The concept of the quark, which is now widely accepted, was a huge challenge to the physics community at the time. The field of particle physics was in a bit of a fog, with scientists debating whether protons and neutrons, two fundamental particles, could be split into smaller components. Zweig, along with Italian physicist Giordano, came up with the quark model almost simultaneously, though their theories had some key differences. Giordano's version leaned more toward the quark as a mathematical model, designed to explain the similarities and symmetries between particles. Zweig, on the other hand, took it further by proposing that quarks were not just mathematical constructs, but actual building blocks of matter particles with real existence, even though they couldn't be directly observed. In May 1964, Zweig and his collaborator Giordano published their work on the quark model. The key point of their paper was simple but revolutionary: particles like protons and neutrons were not the most basic particles after all. They were made up of even more fundamental units, quarks. Quarks, however, weren't standalone particles. They combined in various ways to form the particles we see in the world. Zweig's model introduced three main quarks: up, down, and strange. These quarks combined via strong interactions to form more complex particles. For example, a proton was made up of two up quarks and one down quark, while a neutron consisted of two down quarks and one up quark. The strange quark helped explain some unusual phenomena, particularly the strange particles observed in particle physics experiments. The quark model wasn't just a breakthrough for theoretical physics, it provided a solid framework to explain many experimental results that had previously been puzzling, especially those involving strange particles. Scientists had observed peculiar particles that behaved differently from regular particles in high-energy collisions, and these anomalies couldn't be explained by traditional particle theories. But Zweig's model, with the addition of the strange quark, offered a new and insightful explanation. But that was just the first step for Zweig. He soon proposed the octet model, another theory that gave particle physics a fresh perspective. Based on symmetry principles, the octet model suggested that different particles could be seen as combinations of various types of quarks. He divided particles into 8 basic types, each corresponding to a unique quark combination. This model not only explained the similarities between particles but also predicted the existence of yet-to-be-discovered particles. Despite its brilliance, the octet model didn't get the attention it deserved at the time. Many physicists dismissed it as just a mathematical construct, nothing more than an abstract tool in theoretical physics. But Zweig didn't let that discourage him. He remained confident in his theory and continued to push the research forward. And as they say, patience is a virtue. His persistence would eventually pay off. In 1968, the Stanford Linear Accelerator Center, SLAC, conducted experiments that provided indirect evidence for the quark model. By observing high-energy particle collisions, scientists discovered small particles inside protons and neutrons that resembled quarks, offering strong support for their existence. While the quarks couldn't be directly seen, the experimental data confirmed their indirect presence. This marked the moment when Zweig's quark model began to gain widespread recognition. Though Zweig's theories, including the quark and octet models, weren't immediately celebrated, they laid the foundation for future work in particle physics. Over time, the quark model became one of the core pillars of modern physics, especially in understanding the strong interactions and the relationships between fundamental particles. Zweig's work was a game-changer, even though it took years for it to receive the acknowledgement it deserved. But his theories remain at the heart of particle physics to this day. And as they say, the proof is in the pudding. His ideas were eventually validated, and their impact continues to shape the field of science. When George Zweig proposed his quark model in 1964, many physicists simply couldn't accept the idea of invisible particles. Could something so mysterious really exist? In the world of physics, every new theory must pass through the crucible of rigorous testing, especially when it proposes the existence of particles that can't be seen or directly measured. This wasn't just a debate in theoretical physics, it was a challenge to the very foundation of belief. Let's take a look at how Zweig faced these challenges, and how, in the end, the truth came to light. When Zweig's quark model was first introduced, it sparked intense discussion. The idea of quarks wasn't just innovative, it introduced a whole new concept to physics: fundamental particles that can't be seen. While quarks provided a compelling theoretical explanation in the mathematical framework of physics, the lack of experimental evidence meant that Zweig's theory wasn't immediately embraced by the scientific community. At the time, scientists were used to relying on observable experimental data to back up theories. The existence of quarks, at least when Zweig first introduced the idea, couldn't be directly tested. For many physicists, quarks seemed more like a mathematical construct, a tool for explaining complex phenomena in particle physics, but not something that actually existed in the physical world. Despite the model's ability to explain many things that hadn't been understood before, Zweig's theory was met with skepticism. Even prominent physicists like Nobel laureate Richard Feynman questioned the existence of quarks. Feynman famously said, "Quarks, you can't touch them, you can't see them, you can't even experiment to verify them. Why believe in them?" This kind of skepticism was widespread in the physics community, and many scientists considered the lack of experimental evidence to be the biggest flaw of the quark model. But despite all the doubts and criticism, Zweig never gave up on his theory. He firmly believed that the quark model would eventually provide a clearer and more complete explanation of the workings of the universe. Zweig's dedication to his theory and to the pursuit of scientific truth was inseparable from his academic career. While many colleagues were doubtful, he remained convinced that science would eventually prove the validity of the quark model. Then came 1968, a pivotal moment. The Stanford Linear Accelerator Center, SLAC, conducted an experiment that provided the first indirect evidence for the existence of quarks. This experiment was historically significant. Scientists used high-energy particle collisions in an attempt to uncover the structure of protons. At the time, physicists already knew that particles like protons and neutrons were likely composed of smaller particles, but what those particles were remained a mystery. In the SLAC experiment, scientists bombarded protons with electrons at extremely high energies. This collision revealed the internal structure of the proton, and they found that it contained particles that resembled quarks. The experimental data revealed an important phenomenon: the scattering angles and distribution patterns of the particles were consistent with the presence of quarks. While quarks couldn't be directly observed, the scattering data provided strong evidence that the constituent particles of protons were indeed real and aligned with Zweig's model. This experiment provided indirect evidence for the existence of quarks, marking a key moment in the validation of Zweig's theory. It not only supported the quark model but also laid the groundwork for the standard model of particle physics. The experiment showed that protons weren't a single, fundamental particle, but rather were composed of smaller particles that interacted via the strong force, exactly what Zweig's model had predicted. However, even with this indirect evidence, Zweig's theory still faced challenges. Many in the physics community were still unsure whether quarks could truly be considered fundamental particles. Some believed quarks might still be just a mathematical hypothesis that would eventually be overturned by new experiments. Zweig, in an interview, humorously remarked, "People always want to see them, but the quantum world is just that elusive." Despite the continued doubts and challenges, the quark model was eventually widely accepted. By 1969, with more experiments and theoretical research, quarks became a central concept in particle physics. Zweig's theory gradually gained recognition in the scientific community. Over time, the quark model not only explained the internal structure of protons, but it also provided a framework for studying other particles, like neutrons and strange particles, as well as strong interactions. What's more, the quark model laid the theoretical foundation for future particle accelerator experiments. Major particle physics labs, such as CERN and Fermilab, continued to test the quark model through accelerator collisions, ultimately confirming that quarks were indeed one of the building blocks of matter. As the saying goes, seeing is believing, but in the case of quarks, believing came first and eventually, seeing followed. Through persistence and dedication, Zweig's model was proven right, and his work continues to shape our understanding of the universe today. Though George Zweig's contributions to physics were monumental, he didn't receive the recognition he truly deserved. In 1970, Mario Giordano was awarded the Nobel Prize in Physics for his role in the development of the quark model, while Zweig was left out. But rather than feeling disheartened, Zweig's passion for science never waned. He continued to explore deeper into the world of physics. Yet, he wasn't satisfied with just his groundbreaking work in particle physics. In the early 1970s, Zweig turned his attention to an entirely new frontier, computer science, specifically the field of artificial intelligence, AI. Despite already being well known in the world of physics, Zweig chose to pursue a completely different academic path. His shift wasn't random. In the late 1960s, as computer technology was advancing rapidly, AI was starting to make waves. Zweig, always keen to make connections between different fields, recognized the striking similarity between the challenges faced in physics and those in computer science, particularly when it came to solving complex problems, simulating systems, and predicting patterns. His decision to move toward computer science was less of a sudden change and more of an extension of his lifelong pursuit of understanding the deeper nature of scientific problems. By the early 1970s, Zweig began applying the mathematical tools and theoretical knowledge he had honed in physics to the emerging fields of AI and neural networks. His initial interest in neural networks stemmed from his fascination with how the brain processes information. Though computer power and algorithms were still rudimentary, neural networks and AI had already begun to stir interest in the academic community. But Zweig was never content with simply exploring the standard models of particle physics. He wanted to approach problems on a larger scale, understanding cognition and information processing in ways that went beyond just physics. In the 1970s, research on neural networks and AI was still in its infancy. While there were many theoretical challenges, Zweig wasn't daunted by the limitations of technology. Drawing on the mathematical skills he had developed in physics, he made some insightful contributions about how neural networks process information. His research was more complex than the then popular perceptron model, exploring the intricate interactions between neurons and how these interactions could be used for pattern recognition and learning. In 1972, Zweig proposed early theories that predicted how neural networks could improve their learning processes by adjusting weights and connections, ideas that would later become foundational to deep learning. By 1973, Zweig had started to apply his theories to machine learning, focusing on how neural networks could optimize computational processes and explore the similarities between brain learning and computer programs. He believed that, just like the human brain, computer programs could also learn, train, and optimize by extracting useful information from data. This vision closely aligns with modern deep learning theory, even though the technology at the time wasn't advanced enough to implement such complex systems. Zweig's work in AI, however, didn't receive the same level of recognition as his contributions to particle physics. Back then, AI wasn't the buzzword it is today, and research into neural networks and machine learning was still in its early stages. His ideas, like deep learning and adaptive learning processes in neural networks, didn't spark widespread interest at the time. Yet, as technology advanced, many of his theories found acceptance and would go on to become essential building blocks of modern AI. In 1979, Zweig published a paper on neural networks and machine learning, expanding on how neural networks could mimic the brain's information processing capabilities. While the technology of the time couldn't support the kind of deep learning we have today, Zweig's theoretical groundwork offered valuable insights for the future of AI. Unlike many of his peers, Zweig didn't chase the limelight of the tech revolution. Instead, he quietly focused on his research, dedicating all his energy to his passion for science. Zweig's transition to AI didn't make headlines in the academic world, but his contributions to the field would leave a lasting impact. By the 1980s, breakthroughs in AI and neural networks took place, and the development of deep learning algorithms provided significant momentum for the field. What's remarkable is that the early ideas driving these advancements can be traced back to Zweig's work. Though he never received the same accolades as some of the computer scientists who followed, his research laid the theoretical foundation for AI and deep learning, making him a crucial, though often overlooked, figure in the history of modern artificial intelligence. As they say, success is not the key to happiness. Happiness is the key to success. Zweig's happiness was always in the pursuit of knowledge, and through that pursuit, he contributed to more than one field, his legacy living on in both physics and AI. George Zweig wasn't just a low-key family man, he also forged strong academic relationships with some of the most notable figures in science. These connections played a pivotal role in shaping his later research. Zweig worked closely with fellow physicists Mario Giordano and Richard Feynman, two individuals who had a lasting impact on his career. Giordano, who co-developed the quark model alongside Zweig, was more than just a colleague, he was a trusted collaborator. Their partnership was built on mutual respect and shared scientific curiosity. In the early days of the quark theory, the two had many deep discussions that fueled each other's ideas. This intellectual exchange was essential in refining their theories and significantly influenced Zweig's work. Their relationship is a perfect example of how cooperation and communication can elevate scientific progress. Then there was Richard Feynman, the Nobel laureate in physics legend, who also maintained a friendly academic relationship with Zweig. Though their research didn't overlap directly, Feynman's work in quantum electrodynamics was a different field from Zweig's quark model. Their interactions broadened Zweig's intellectual horizons. Feynman's wit and creativity left a lasting mark on Zweig, encouraging him to trust his intuition and embrace the creative side of scientific exploration. Their friendship also provided Zweig with a solid support system, especially during challenging times when Feynman's encouragement helped keep him going. These academic connections and personal bonds were more than just collaborations, they were sources of inspiration that fueled Zweig's scientific journey. Despite his reserved nature, Zweig's work was enriched by the partnerships he built within the scientific community. As the saying goes, if you want to go fast, go alone. If you want to go far, go together. Zweig certainly went far, and his relationships along the way played a crucial role in his enduring legacy in science. Today, George Zweig's name might not carry the same fame as Einstein or Hawking, but his contributions to science are undeniable. Every time a particle accelerator hums to life, we're still tracing back to his groundbreaking quark model. Zweig's theory didn't just lay the foundation for the standard model of particle physics, it fundamentally changed how we understand the building blocks of matter. Zweig introduced the concept of the quark, a new kind of particle that explained the makeup of protons, neutrons, and other strong-force particles. When he first proposed this model, it wasn't met with universal acceptance. But over time, the quark model evolved into one of the cornerstones of modern physics. Today, global particle accelerators, like CERN's Large Hadron Collider, are built on the very framework that Zweig pioneered. The quark structure inside protons and neutrons, and the strong interactions between them, remain central to ongoing research in particle physics. But the quark model didn't just revolutionize theoretical physics, it provided practical guidance for the design of particle accelerators. By accelerating and colliding high-energy particles, scientists have observed more and more experimental results that align with the quark model. These findings not only confirmed the existence of quarks but also drove the development of the Standard Model and particle physics as a whole. Zweig's work has become an indispensable part of modern physics, laying the groundwork for many subsequent discoveries and theories. Zweig's influence didn't stop at particle physics. In the 1970s, he turned his attention to computer science and artificial intelligence. His early research on neural networks and machine learning laid the theoretical groundwork for what would later evolve into deep learning and modern AI. Though his contributions weren't widely recognized at the time, as computer science rapidly advanced, Zweig's cross-disciplinary work provided a theoretical foundation that's still influencing the AI field today. In many ways, today's deep learning algorithms trace back to his early ideas. What really sets Zweig apart was his interdisciplinary approach to science. He wasn't just focused on breakthroughs in physics, he was eager to explore and challenge unknown territories in other fields too. His work exemplified a deep understanding of science. Progress doesn't belong to just one discipline. It thrives when ideas collide across different fields. Despite never winning a Nobel Prize, Zweig's legacy is firmly etched in the history of science. His quark model didn't just transform our understanding of particle physics, it provided the theoretical foundation for modern particle accelerators. His early work in computer science continues to have a profound influence on the progress of AI and machine learning. Zweig's academic legacy reminds us that the true value of science lies not in the accolades, but in the pursuit of knowledge and truth, a force that drives humanity forward. Though he never received the Nobel, Zweig will always be a hero in the history of science, and his contributions will keep shaping future discoveries and technological innovations. As the saying goes, the road to success is always under construction. Zweig may not have won all the awards, but his path of exploration and innovation laid the groundwork for countless others to build upon.
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.